Hello, tonight our video is on rate of change again. This is part 2. So consider the graph in front of you. Here we have a graph of where the y-axis represents distance in miles and the x-axis represents time in hours. Let me go ahead and label those. Here's your x-axis, here's the y-axis. Alright, so looking at this graph, we could write a rule based on these points that are given. All right, so our rule is going to be the dependent variable y is equal to something x and then plus something. All right, so let's look at the value of y when x is 0. Just like in a tile pattern, we would look at the number of tiles in figure 0. Well, looking at our graph, when x is 0, the value of y is also 0. The distance traveled is at 0. So we would put a plus 0 there, or we could just leave it off, but that's what would go on this part of our rule, right? The initial figure, if this was a tile pattern, would have 0 tiles. But this is not a tile pattern. This is just a graph of something traveling over time. So the initial value would be 0. Now, that's not really necessary to leave it in our equation, so I'm going to go ahead and erase it because any number plus 0 is not going to change. Now let's look at the rate of change, the amount that the distance goes up by for every one value of x.
Mrs. Schmitz, please call extension 2002.
Okay, so looking at the amount of change, when x changes from 0 to 1, right here, the value of y goes up from 0 to 5. And then as x changes from 1 to 2, the value of y goes from up 5 from 5 to 10. So it looks like every time x increases by 1, the value of y increases by 5. So if this was a tile pattern, it's increasing by 5, plus 5 in the y direction. And it's not a tile pattern, it's a graph of something traveling, but it's still the same idea. The increase is 5 for every 1 hour. So the growth factor is going to equal 5. The number 5 would go right here in front of the x. So this is the graph of the equation y equals 5x. So therefore, if x equaled 4, y would equal 20, right? And it would be right here on our graph. All right, now consider this graph. Here we have two line graphs representing distance traveled again in hours, and they're two different bikes, so two different bicyclists, bike A and bike B. Notice that they both have the same initial distance traveled. Before time starts to go by, they're both at 0. All right. So let's look at the two graphs and let's find the rate of change for each graph. Let's start with the red one. All right. So I can see here that when 5 hours passes, right here, so after 5 hours, the bike A would travel 1 mark above 50. So that's going to equal 60 miles. All right. So let me write that down. Bike A traveled 60 miles in 5 hours. Now this is a straight line, so the rate of change is going to be the same everywhere. All right. And let me double check that. Let's say that bike A traveled for 10 hours. Then the distance it covered would be up here. That is 2 marks past 100. That's 120. All right, those two ratios should be the same, and they are. They both reduce, if we're going to put this as a rate, they both reduce to the same number. They both reduce to 12 over 1, or just 12. So the rate of change for the bike A is going to equal 12. So that means that bike A was traveling at a rate of 12 miles per hour. 12 miles every 1 hour. Now let's look at bike B. Bike B, after 5 hours, travels a distance of 40 miles. And again, it's a straight line, so after 10 hours, it travels 80 miles. So what would be the unit rate or the rate of change for bike B? Well, if you said 8 miles per hour, you would be correct. All right, so let me write that. All right, so notice that bike B is traveling at a rate that's lower than that of bike A, and therefore the line is less steep. It's a little bit flatter. And that bike A is traveling at a higher rate of speed, so that line is a little bit steeper. Read some books.